Okay, so last week I promised that all the integration that we had to do to work out what the shear stress was in the structure was a short-term problem. I kind of lied a little bit. It's something that you will have to do generally if you want a more accurate solution, but today I'll show you some approximations that we can use to make the calculations a lot simpler. And we generally refer to this as structural idealization or structure idealization. So this is a standard straight wing aircraft cutaway. Okay, there's nothing particularly special about this aircraft. It's pretty generic. You can see that we've got here a couple of spars. Okay, we've got frames that we're all familiar with. We've got longerons and stringers and skin everywhere. Now, obviously, we can take sections at various places and try and work out what the stresses are in those sections, but the structure is pretty complex. If we were to go and try and integrate all the way around this structure to try and work out what the shear stresses were everywhere, we would be here for eternity. So we need some simplifications. And again, this is a bit more of a closer view at pieces of structure. So up in the top left here, we have a wing box or a wing cross section, and the wing box is defined, remember, by the front spar, the skin, the rear spar, and the skin. This is what we call the wing box. Okay, it's a box shape. And the reason we have boxes as opposed to open bits of structure is that they're, as we learnt last week, much better at resisting torsion than an open section. So we have closed cells generally in our wings. Now, again, that's a fairly complicated bit of structure. And if we were to try and solve it the way that we were doing last week, we would have to integrate around and work out what the shear stress was on all these little features. So if we were down here, we'd have to do an integration and work out what the stress was on all the little features as we went around, and we would have an incredibly complex task on our hands. So we have an idealization strategy. And that idealization strategy relies on breaking the section up into discrete units. So instead of having a distributed tensile stress or a distributed shear stress, we break the structure up into what we call booms, which are these little discrete bits of load-carrying structure, and panels. Now, the assumption that we make is that the booms carry all the direct stresses. So all the tensile and compressive direct stresses are carried by the booms, and the panels carry all the shear stresses. So anything that is in shear is carried by these panels. Anything that's acting in tension or compression is carried by the booms. And it's really an area idealization. So because we remove all the direct stress carrying area that's here, this cross-sectional area, we clump it into two booms. And the material in between, we assume, because it doesn't carry any direct stresses, there can't be any variation in tensile stress across that regime, across that distance. Now that solves a few problems for us. The first is that we can take problems like this, where we have stringers and skin and all sorts of problems, and collapse them into booms and panels. And generally, when you see a 2D drawing like this, the booms are represented by little dots, and the panels are represented by little straight sections, just like skin. Now, we have to remember that these are not real structures. They're just they're an idealization trick. They're a tool that we use to to make our calculations a bit more easy. If I see in the exams that you say, if I ask you what a piece of aircraft structure is and you say a boom, then that's automatically incorrect because there is no such thing as a boom in aircraft structure. It's really just a trick that we use. Okay. Now, if we look back at this for a second, we've done this idealisation that I've shown here actually achieves two things. It takes all the area from the skin and it clumps it into a boom. So all the bits of skin area that are around go into the boom, and so do the stringer areas. So when I ask the question, where do we idealise? The answer is that if there's any stiffening structure, such as a stringer or a spar cap, we should idealise our area to there because it makes our calculations a lot easier. If there's no stiffening structure, then we can still idealise, but we just have to pick somewhere that we choose. But generally, in most aircraft structures, it's a reasonable assumption to just pick the stiffening structure as the place to idealise. Now, let's take a little bit more of a detailed look at how we do that. If we have a bit of structure like this, we have our front spar, and these are all labelled on the diagram if you want to look along here, a main spar, and in this case we've actually got a 3-spar configuration, so there's a rear spar as well. And we have these little bits of built-up structure called spar caps at the end of each spar. We have Z stringers on the tensile surface and J stringers on the compressive surface. Now if we just zoom in on one section there, so if we zoom in just at the bottom wing skin there, then you can see that there's some material in the skin. So there's some material here, and there's some material in the stringer. Now our idealisation collapses all of that area, so we've taken a section, remember all these calculations are done on a section. All the cross-sectional area is collapsed to, for each stringer is collapsed to a boom. So we take, I'll see if I can colour code this. We take all this skin area and this stringer and we collapse it to this boom. We take all this red and collapse it to this one. And let's just pick another colour, orange for instance. Okay, and we collapse it to that one. So the area of the boom, which we use a symbol for, which we use the symbol B later on, the area of the boom is the area of the skin that's collapsed, so the skin that's in between the stiffeners, plus the area of the stiffener is collapsed into that boom. And we assume that the thickness of the skin that's left over, I use the subscript D there, TD, which means the thickness of skin that carries direct stresses. So the direct stress carrying skin is 0. When we calculate shear stresses, we need to account for the real thickness, but for direct stresses, we assume it doesn't exist. Now, let's look at our process for actually doing the idealisation. Okay, so I'll put some variables on our diagram, and this picture is directly out of Megson, so you can follow along if you've got a copy of it. It's also in your notes. Now what we're going to try and do is work out the equivalent areas of these booms so that we've got a representative structure. So on the left we've got the real structure, which has got a varying stress across it. It has a thickness T and it has a width B. And what we're going to try and do is collapse that into two booms which have area B1 and B2 that have the equivalent external reactions. So if we took sum of forces or sum of moments, everything would be the same. Internally, we've changed things, but we want to make sure that the response of that structure globally is the same. Okay. So the way we do that, I've actually written up the calculations in the OneNote notes if you want to follow along, but I'll write them on the board as well. Okay. So what we're going to try and do. Let's close that door. Is we're going to try and say that the left-hand side and the right-hand side are equivalent. Okay, so when I do these equations, the left-hand side is going to be the forces from the left, and the right-hand side is going to be the forces from the right, and vice versa. Okay, so the force acting on the plate on the left-hand side is the average stress. So the average stress is sigma 1 plus sigma 2 on 2. Okay, the average stress times the thickness times the width. Okay, so that's the total force it's pulling on the end of the panel. On the right-hand side, we've got sigma 1 B1 plus sigma 2 B2. So these B's are areas, okay, so they're the area of each boom. And remember, again, these are just virtual areas. They're not real, they're just a virtualized area. Okay, so we've got two unknowns here, so we can't solve yet. We've got two unknown areas. Now, what else could we use to find the... If we need a second equation, what do we generally rely on as the next equation? Moments, yes. Sum of moments. Now, sum of moments is a little bit trickier. For the sum of moments, I'm going to do a little bit of a trick. Okay, what we're going to do is, on that diagram up there, there's sigma 2 acting at one end, and there's sigma 1 acting at the other end, and there's a linear variation in between. We're going to break that up into a rectangle and a triangle just to make our moment calculations a little bit easier. And so the rectangle has magnitude sigma 2, and the triangle at its long end has magnitude sigma 1 minus sigma 2. And we're going to take moments about, where are we going to take moments about just to make sure the calculation here is right? We'll take moments about B2, okay, about the second boom, which is here or here. So the moment from the rectangle is the force from the rectangle, which is sigma 2 times T times B. Okay, stress times area. And what's the moment arm of that rectangle? B on 2. Okay, so it's acting halfway along. And the moment from the, we're going to use, if we put the right hand rule vertical on we're going to use sort of right hand positive. Okay, so moments this way positive. Okay. Now, the moment from the triangle is the average stress times the thickness times the width. So that's the force. And the moment arm, what's the location of the moment arm for a triangle or the centroid? It's 2/3 from the narrow end or 1/3 from the wide end. So from the point we're interested in, it's 2/3 B. Now on the right of this equation, what's the moment we've got there? Sigma 1, B1 gives us a force, times B gives us a moment. Okay, so now we can solve for B1 here. And once we've solved for B1, we can substitute it in there and solve for B2. Now, first thing I'm going to do, I'm going to start with this equation so we can solve for B1. First thing I'll do is get rid of a B out of every side. So I'm going to, because I've got limited board space here, I'm just going to manipulate it on the board so you can write out the correct thing in your book if you want. I'm just going to take away a B from every term. Okay. So every term here has a T and a B in it. So I'm going to bring them out the front. And I'm also going to bring a 6 out the front. Okay, because I need to get rid of all the bits on the bottom. So in here I'm going to have 3 sigma 2. From this term I'm going to get, there's a sigma 1 times a 2. So 2 sigma 1 minus 2 sigma 2. So when I rearrange, B1 equals TB on 6, 2 plus sigma 2 on sigma 1. Okay, and that pen's useless. Now, without doing the substitution, because the substitution's in the notes and I don't think it's particularly useful for me to do it again. And we can see by symmetry, if we want to be tricky about it, that to find B2, all we have to do is switch sigma 1 and sigma 2 around, because by symmetry that has to be the case. Now if you add those two together, you can prove to yourself that we've got the top equation holds, but now, remember this is a direct stress calculation, and we're talking about stress varying from direct stress. And the primary reason that will give us varying direct stresses is bending. If you think about if we just apply a net tension to a structure, the direct stress should be constant everywhere. The thing that causes variation of direct stresses is bending, because you've got tension at the top, or sorry, compression at the top for a normal wing, tension at the bottom, and you've got a variation in stresses as you move around. So if we think about a bending calculation, our sigma bending for a simple symmetric problem is my on Ixx. So the bit in here that we're interested in, sigma 1 over sigma 2 or sigma 2 over sigma 1, okay, so for bending problems, or problems where there's just bending and shear and no tension or compression, it's a very easy thing to calculate this ratio of stresses, because the only direct stress we're going to get varies, the stress varies linearly with position. So if we take the ratio, we just need the ratio of the positions from the neutral axis. So let's do an example of that idealization procedure. Here we have a fuselage cross-section, so a big barrel fuselage with a thickness that's 0.8 millimeters of skin, and we've got these stiffeners everywhere, and I haven't got the stiffener areas. I think they're 200 millimeters squared. Let me just check in the problem. Now this problem is actually from another chapter in Megson, if you're following along, because we're going to use it to do another calculation. Okay, so the area of each stringer is 100 millimeters squared. Now what our aim is to take the structure that's on the left with the positions of all our stiffening elements and the skin and turn it into an idealized boom and panel problem on the right. So on the right we've taken every stringer location and turned it into a boom. And the stringers are evenly placed around the barrel. And you can see via the picture on the left that the radius of the barrel is 381 millimeters. So this problem is perfect for a tabular problem. Okay, we know that these B's, all we need to find the B's are things like thicknesses and ratios of Y positions. So we will use a table like this. So let's just work out what we're going to do here. So at each stringer, we have three things that we need to put in. So let's just call this the stringer of interest here. Okay, and that stringer has an area A. Now there's a panel to one side and a panel to the other side of the stringer. So when we're working out the area of our boom, the area of our boom is the area of the stringer plus the area from panel 1 plus the area from panel 2. So let's just do this for the boom 1, for the top boom. Okay. Now, just be a little bit careful. I've used B. I'm going to use B for boom here, but it's not the same as the B up there. Well, it is the same B, but just this, the subscript 1 here is not the same as the subscript 1 here. So the A of the stiffener is 100 millimeters squared. The A from the panel to the left is the thickness, which is 0.8, times the width of the panel to the left, so that we're talking here about the panel 116 here. Okay. The width of that panel is 149.6 because all the stringers are evenly spaced around. On 6 times now, let's look back at our little diagram here. If we assume we're at B2, if we're assuming we're calculating B2, then the ratio here is sigma 1 over sigma 2. If we're calculating B1, then it's sigma 2 over sigma 1. So the stress, the position of the boom is always on the bottom, and the position of the neighbour is always on the top. So we've got 2 plus y16 over y1 plus, again, 0.8 times 149.6 over 6. 2 plus y2 over y1. So let's do that calculation. If anyone's got a calculator, y16 and y2 are the same. They're both equal to 352. Has anyone got an answer? 216 is right, because I have the answer in Megson. Okay, it's one of the few times that I can be confident that someone in the class has got the right answer. All right. Now, just so we know we've got the technique down pat, I'll do B2, which is 100 plus 0.8 times 149.6 on 6, because these are equally spaced. All the panel spacings are going to be 149.6. 2 plus y1 over y2 and I'll chuck the next bracket in here as well, plus 2 plus y3 over y2. So the boom we're trying to work out is always on the bottom here. And the neighbours are on the top. And this also should equal 216. Or it's 216.6, I think, but 217. Okay, and if you go around, you'll find out that they're all equal to 217. Okay. And the reason we put it in a table, we'll see in a minute, it makes it very, very easy for us to do bending calculations and other calculations when it's in a table. Okay, so why does this help us in any way, shape or form? Well, now we've got discrete areas. Remember last week we had to do integral of t, y, ds. We don't have to integrate anymore because all of our areas clumped together. Everything can be done with sums. No integration, just sums of things. So tables become very, very helpful. It also makes our IXX calculations really easy because now we don't have any BD cubed on 12 terms. Everything is just an area times a distance squared. So IXX calculations are really easy as well. Now, for this fuselage problem that we've got here, we're going to do a couple of different calculations with it. We're going to calculate the bending stresses, we're going to calculate shear stresses, and then we're going to put them all together. Now, bending stress calculations are exactly the same as they were before with this idealisation, except some of the bits in the calculation are easy. So, if you had to calculate the IXX of this before, you would have had to know what the IXX formula for a thin shell circle was, and then the IXX for each stiffener, and add them all together. Now the IXX calculation is just a sum of by squared. Okay, an area times the distance to the neutral axis squared. As long as this is the distance from the neutral axis and not some other distance. And in the problem we've got there, the neutral axis is the center of the problem. So what we're going to do is we're going to take the previous geometry for the fuselage and apply a 200 kilonewton, a positive 200 kilonewton bending moment to it. So now we extend our table a little bit, so hopefully you've left space at the side of your table. And we can put the IXX contribution for each boom, and then we can sum up, and then we can work out what the stresses are. Okay. So let's fill in. Just write down what the columns have to be, and I'll go back to the picture so we can look at the picture. Okay, so you need 5 column headings. The y here. What? Sorry, that's not a subscript. That's like y. Sorry. Okay, so let's go back to the picture. So we can put in all our y's. If I 1, 2, 16, 3, 15. I'm not going to write all of the all of the subscripts in. Now, the top one is 381. 381, 352.0. We're getting a bit silly with our significant figures here. 269.5. 145.8. The next one is 0. And then there'll be minus 145.8. Minus 269.5, minus 352, and minus 381. Now, area for all of them is 217. And that's in millimeters squared. Now we're going to look at the IXX contribution for each one individually, or for each row. Now for the top row, that's 381 squared times 217. For the next one, because there's two elements, we have to double it because there's two stringers at each position. So for the top one, it's just AY squared, or BY squared, where B is the boom area. Okay. I'll sort of interchangeably use B and A, I'm sorry. And the bottom one, number 9, which is down the bottom here, we only use a single again because there's only one at 9. All the others have 2. This one has 8 and 10, and they're all doubled up. Okay, so has someone got this first term in here? 217 times 381 squared. (22 by 10 to the 6). Is anyone else advancing on that? Nope. Okay, the next one, remember we've got to double it, so it's 2 times 217 times 352 squared. (54 by 10 to the 6). Okay, and you can keep going. Now the bottom ones should be the same as the top ones because when we square, the negative sign disappears, so everything down the bottom should be the same. So we should have a 22 by 10 to the 6 down the bottom, and a 54 by 10 to the 6, and the middle one's going to be 0 because its y is 0. So we've only got to calculate 2 more, and then we've got the whole table filled out. So let's do that. 2 times 217 times 269.5 squared.
For the IXX for boom 1, isn't it 318 squared times 217? Yeah. 314,99937? I think the answer is wrong.
31.5 10 to 6.
Okay. Sorry, but no one put their hand up when I asked if you had another answer. So. Yes, okay. So what have you got for it? 31.5 by 10 to the 6. Okay, you got to speak up if you see an answer up there you don't agree with. What about the next one? Is that one all right or not?
Yes.
Yep. And the next two, we only need two more.
It's 31.5 and then 9.2.
31.5 by 10 to the 6 and 9.2 by 10 to the 6. And the same again on the bottom. Okay, so this is the IXX contribution from boom 1. This is from 2 and 16. So the total IXX is just the sum of the whole thing.
$252.
252 by 10 to the 6. And we're in millimetres to the 4th there. Okay, so the next column heading was sigma z, and we're going to do it in megapascals. Okay, if we use newtons and millimetres, we'll get megapascals out as a stress. So how do we calculate that? Well, we know that the stress is equal to my on IXX. Okay, m we've been told is plus 200,000 Newton meters. Okay, so let's get that into units that we can work with. M equals 200,000 Newton meters, and 1 meter is 1,000 millimeters, so that's 200,000 Newton millimeters. Which is 2 by 10 to the 8. Newton millimeters. Our y is already in millimeters. So on top we're going to have Newton millimeters. So we're going to have Newton millimeter squared divided by millimeters to the 4th is going to give us newtons per millimeter squared. Now, positive moment is going to give us a positive stress at the top and a negative stress at the bottom, which means we've got tension at the top and compression at the bottom. So we can go through and calculate each of the stresses. We'll just do a couple. So the top one, 2 by 10 to the 8. Times 381 divided by 252 by 10 to the 6. And if you're doing this repetitively, it's good to calculate the value of this so you don't have to keep multiplying by m and dividing by IXX. That's not going to change through each of your calculations. So if you just work out that as a number, you can just keep multiplying it by y. Yep, 302 megapascals. So the bottom's going to be minus 302 megapascals. All right, and I'll leave you to calculate all the rest, but they're all on page 644 of Megson if you want to follow along. Okay, so that's a bending stress calculation. So we now have gone and we've calculated the stress all the way around a fuselage in the space of, I don't know, 20 minutes or so for that station of the fuselage. So if we tried to do that calculation where we'd accounted for all the little geometries of the stiffeners and everything and the IXX for the shell, that would have been a much harder calculation to do. Admittedly, we only have the stress at a few discrete locations. We don't have a formula that tells us the stress anywhere, but we can interpolate later on if we need to. If we want to know the stress somewhere in between 15 and 16, say, we can interpolate. So we just worked out how to calculate bending stresses with our idealisation approach. Now we're going to look at shear stresses. So remember the direct stresses, so bending stresses are a version of direct stress. Those are carried by the booms, but the shear stress is carried by the panels in between. So our shear stress calculation is going to rely on the panels. Now if we look at a picture of an open cross section this time, so just to make our calculations a little bit easier, we'll just consider an open case. Now, if we imagine that these booms run the length of the fuselage, so instead of looking at them 2D now, I've just twisted around so we can see the 3D view of them. There's going to be some stresses acting on them. So at one end of the boom, there'll be this sigma z that we've calculated. The other end of the boom, there'll be a change in that sigma z. Okay, so that sigma z will go to d sigma z dz times the distance that we've travelled. And the forces that will bring about that change are the shear flows acting along the side of the boom. So if we look at the free body diagram for the boom itself, which is just this bit, there's forces acting on each end and then there's forces acting on the sides due to the shear flows. Now the benefit of this technique, remember last week in our calculations we had this integral ty ds in our calculations. Now because we've assumed the thickness of the panels is 0, the shear stress between there's no change in this. If t goes to 0, wherever t is 0, there's no change in that integral. The only place the shear flow changes is when we cross over from a boom into the next panel. So for any panel, the shear stress is constant, or the shear flow is constant. So now instead of having to integrate to work out what the shear flow is at any point, all we're doing is we're doing a series of sums to work out what the shear flow is in each panel. If we do a sum of forces calculation for our boom here, the tensile stress or the tensile force on the front end of the boom is the stress times the area. On the other end of the boom, it's the stress times the area. And along the edges of the boom, it's a shear flow times a length. So these are all force terms. Remember, shear flow is newtons per millimetre or force per distance. If we multiply by the distance over which it's acting, we get to a force. So stress times area, shear flow times distance. So this the forces should equal 0. And if we rearrange, we end up with this. That the difference between the shear flow in panel 1 and panel 2, so this is 2 over here and this is 1 over here, the difference is related to the change in bending stress along the boom. Now, this should look fairly familiar. This term here, we've seen this term before. This term we can substitute in our more general complex relationship for the change in stress. And for the case that we normally consider when Sx and Ixy equals 0, the formula drops out to this. Okay. So before we had Q minus Qs naught equals minus Sy on Ixx, the integral of Ty ds. Now we've got Q2 minus Q1 equals minus Sy on Ixx. What's left? Tb. Sorry, not Ty. Where I've just denoted subscript r to say it's the r, it's the rth boom that will cross. So there's some equivalence here. This is tracking the Q that we're trying to find against some starting point that we should know. And here it's the same again. If we want to find Q2, we have to find Q1 first. And the bits in here are sort of similar too. So if we assume y is constant, then integral T ds is an area and b is an area. So there's some similarities here. We haven't completely reinvented the wheel. We've just changed an integral calculation, a distributed calculation, into a discrete calculation. And as with the other open problems, we can start at a free edge. So at a free edge, there's no force on one side, so we can work out what Q1 is. So there's no force on the other side of the boom. So if we cross boom 1, so we go from having Q equals 0 out here in space to work out what Q1 is. When we cross that boom, we can work out Q1 is here. Okay. That's the formula there. Now if we go from Q1 to Q2, we have to cross another boom. So if we go from Q1 to Q2, we end up with Q2 minus Q1. And in this case, it's the area and the position of boom 2 instead of the area and position of boom 1. Okay, so if we rearrange, we get Q2 is the change plus the Q1 we had initially. And if we substitute that in, we get B2, Y2, B1, Y1. So we'll see that if we cross n booms, we can actually get back to our original calculation. So if we want to work out the shear flow in the nth panel, we can say the shear flow in the nth panel minus the initial shear flow, which for open problems is 0. For closed problems, we have to calculate another way, is equal to minus Sy on Ixx times the sum of BR, YR instead of the integral. So we've turned an integral calculation into a sum calculation. And it may not seem like that's a big change, but that makes our life a lot easier in the mathematics. the most general version of the formula, and this is the one that I put on exam formula sheets, is this one. So you have to know, if you want to use specific versions of the formula like this, you have to know how to collapse the big formula. This is the most general version. This is where we've assumed that both the skin is carrying shear stresses and direct stresses, and all we've idealised is the stiffeners. So if we've idealised the stiffeners but left the skin being able to carry shear stresses, then we still have to do our integration, but we also have to include the change as we cross over our stiffeners. So this would be in the case where you've got a stiffener like that, and instead of doing the full calculation for the stiffener, you leave the skin thickness in place and do the full skin calculation, but you put a boom in to represent the stiffener, where B equals the A stiffener. Okay, so this is the most general version. And obviously, depending on the loads, a lot of that drops out. Okay, I have a picture that hasn't loaded here somewhere. I don't know why that's dropping out, but anyway. Okay, we'll do an example in a second, but I just want to show you some properties of this shear flow before we do our example. Okay. Now these panels that are between booms, so in our fuselage problem, we've got all these panels in between booms. And those panels have a constant shear flow in them for the length of the panel. So this panel doesn't have to be the same as this one, and in general it won't be, but within each panel the shear flow is constant. Now there are some nice consequences to that which make our life in some cases easier. If we're trying to do sum of forces or sum of moments calculations, and there's very simple ways of representing the force that's from one of these. So I'll just simplify what we're looking at for the moment here. If we call this position 1 and this position 2, and I'll call this Q12, which means Q in the panel from 1 to 2, then we can break the net contribution of force from this, S in the x direction and S in the y direction, because you imagine if you'd want to know sometimes, you wouldn't actually need to know quite often, what the net shear force from that shear flow is, then it's very easy to do in this case. We don't have to do any integration, we don't have to do anything special. It's just Q times the change in x position. And the y shear force is just Q times the change in y position. So that means regardless of how complicated the shape of this panel is, if I was to draw a wiggly panel in here, the total x force and the total y force from that shear flow is only dependent on the end positions. It has nothing to do with the shape of the panel in between. So that makes our life a lot easier for some calculations. And the moment about a particular point is based on the torque formula we learnt last week, which is 2AQ, okay, 2 times the enclosed area, where the enclosed area, if we're trying to find moment about this point, the enclosed area is all the area enclosed by this here. Okay. So in the drawing I've drawn up there, the area that I'm talking about there is all the area in this shape. Okay, so let's do a simple, we'll do a simple shear flow problem, and then for an open section, and then we'll learn about closed sections, and then we'll go, we'll try and do our fuselage problem, because our fuselage is a closed section. Not, generally not. No, you have to know, you don't have to derive the big versions of the equations. You have to know how to get from the complicated version of the equation to something simpler if you need to use it. But you don't need to derive the big complex version of, you never have to derive that. So, any derivation that would be in the exam would be very much based on first principles. So there'd be a problem, I'd ask you to draw a free body diagram, and based on a simple free body diagram, tell me what the force in a certain member would be. And it might have 1 or 2 steps of derivation, but we're not deriving these big first principles formulae. So let me just go back to our calculation we're going to be interested in here. Now last week we did a C-channel problem, and I can't remember the exact dimensions I gave you, but we went through the process of working out what the shear flow would be and what the shear center calculation was. Now generally the first step of this process is to idealize this somehow. So there are lots of ways we could idealize that section, and you know the basic formula now of how to do it, but you still get a choice as to where to put your booms. So you could theoretically put your booms just in the corners like that. Or you could, if you wanted to, be fancier and put more booms in at various places. Okay. And obviously this is a continuum problem. We've got lots of integrations here. Things are going to change linearly, and then they're going to be parabolic. Okay, there's a continuum problem here. Here our shear flows are constant. Okay, there's no variation in this. So the more points we put in, the more resolution we've got of the things that we're actually trying to find. So if we're trying to find, for instance, the shear flow, the maximum shear stress, then we may need some closer to the place of interest, to work out what the shear stress is going to be. Okay, so you see the more points we put in to approximate, the closer we get to the real problem. But for the sake of our calculation, what we're going to do is we're just going to do the simple one here, just because it makes our maths easier. We don't have to do too many steps. Okay, and the example I'm going to do, just because I've got the numbers in front of me and I don't have to wait for too long, is example 20.3 from Megson. Okay, so we'll just go step by step through that problem. So as with all problems, we need some way of numbering so that we can work out what we've got, what we're doing. We're going to assume S, we start our calculation at 1 and move around, so our S is travelling to the left is our assumption. We've got a 4.8 kilonewton force applied, and the reason I've drawn it out here, why would I have drawn it out to the left there? Yeah, I'm applying it at the shear centre. Because if I don't apply it at the shear centre, I induce all sorts of weird twist in this that I don't want to calculate. So we always, for open sections, or nearly always, assume it's at the shear centre. And the last thing we need are some dimensions. Okay, so we've got, it's 400 deep and 200 wide. Okay, so what's the IXX for this problem? because all of our booms are the same distance from the neutral axis, we can calculate the IXX very, very quickly. 4, because there's 4 booms. 300 is the area of each one, and 200 is the distance from the neutral axis in each case. So in all of these calculations, IXX is the first thing you've got to do. Or find the centroid. If it's not symmetric, you have to find the centroid, but it's not common that I'll give you a non-symmetric problem. So, how do we start? Well, we've got our formula up there. Okay, and one other thing you could possibly put in there to make it a bit easier to interpret, you could put a subscript n in here, okay? Because what we're really finding with this formula is the shear flow after n booms, so in the nth panel. So what can we assume about QS naught for this problem? It's 0. We've got a starting point where we know it's 0. Okay, our starting point is out here somewhere. We know the shear flow is 0, so we can get rid of that bit. So Q1, and what will make our life easier is if we label these. Just so we can more easily refer to our diagram rather than relying on subscripts. It's always a good idea to draw all your labels on. Q1 equals minus 4,800 on 48 by 10 to the 6. And wasn't Megson nice to use something that would cancel out so nicely? Okay, and that's going to be constant for all of the problems. So you can, if you're doing these problems, it's good to calculate that first, because that doesn't change. Now let's interpret what we've got here. We've got sum of r equals 1 to n of br yr. So in our case, we've only got one boom that we're crossing. We're starting out off the panel and we're working out Q1. So our sum is just b1 y1. Where what's B1? 300. What's Y1? 200. Okay, so we can work out what Q1 is here. Minus 6 newtons per millimetre I've got. Now, I've just looked at Megson and I've noticed that his notation is a little bit different in some places. So you'll also see this written as we did last week as Q12, which means Q in the panel from 1 to 2. Just like last week, we sometimes use 2 subscripts here. So Megson actually uses this notation, Q12, Q23, and Q34. Okay. Whatever notation you use, I don't mind. As long as you're consistent, it all falls out. You've just got to be aware of what you're actually calculating when you... And so if you draw it on the diagram, I can immediately see what you're calculating in your formula. If you leave it ambiguous and you make a mistake, it's pretty hard for me to give you sort of part marks for the question. Okay, I'll do the next one. So Q23 minus SY on IXX, sum of BR, YR, where R is varying from 1 to N. Okay, where N is the number of booms we cross over. So in this case, it's minus SY on IXX, B1, Y1 plus B2, Y2. Which we can calculate fresh each time, but often it gets a bit tedious to calculate this fresh each time. So what we can do is separate this into 2 parts. Minus SY on IXX, B1, Y1, minus SY on IXX, B2, Y2. Now the reason we would separate that is that this we've already calculated. This is Q12. All right, and for each time you go to the next boom, the previous bit of the sum is just the you only ever have to calculate the new BR, YR every time you cross a boom. So Q34 equals Q23 minus SY on IXX, B3, Y3. Okay, so each time you're just calculating not a sum, but just each term. So if you've done this calculation, this one should equal minus 12, and this one should equal minus 6. Okay, so that's what the resulting shear flows in the section would look like. Now a quick check. How would we quickly check whether we had potentially the right solution here? And it's to do with this slide. How would we quickly check that we had the right solution? Remember, the external shear force that was applied was 4.8 kilonewtons. So if we're looking at SY, if we're looking at the internal, we've got no Y from this one, no Y from this one. The only Y force comes here, and that's 12 times 400, which, wouldn't you know, is 4,800 newtons. So it's a quick way of checking that our internal forces equal our external forces.
For the Q value, so do you only take the Q that's moving in the y direction?
For this one, yeah, so we could have said SY equals Q12Y plus Q23Y plus Q34Y, but the Y components of these ones go to 0.
So then in that kind of section, would you only take the y? Like, how would you separate the y?
Oh, in the curve section, so we've got straight sections here, but in the curve section it's only just the distance, it's the y of the end point minus the y of the beginning point. So the curve itself doesn't matter, it's just the change, it's just the change from one end to the other. Yeah. So the calculation would still, or the force calculation, it wouldn't actually matter if these were straight or curved. Okay, if these were curved, as long as the booms are at the same places, the calculation still works. When we did our calculation here of our open section problem, we relied on the fact that QS naught equals 0, and I'm going to ditch this stupid pen. Okay, we relied on that, but if this was a closed problem, we can't do that. There's nowhere to start. So what do we do to solve that? Well, we do exactly the same as what we did last week, and we use a moment equilibrium to work out what our unknown shear flow is. So the top is the shear stresses, where we have shear flows, sorry. Okay. Where the shear flow we're trying to, hi Stuart. Where the shear flow we're trying to calculate is this QS. QB is the open section shear flow, the one that we worked out last week when we make the virtual cut in the section, and QS naught is the value of the shear flow at that cut. So if this is our problem here, and hopefully one of my black pens is working. Last week, if we had a box, we would have made a virtual cut on the edge of the box and worked out the shear flow as we went around the loop. Now, the benefit of our idealised calculation is that once you make a cut in the panel, what happens to the shear flow in the entire panel? Well, the shear flow in the entire panel is constant. So if we make one point 0, the whole section goes to 0. So when we make our cut, Q in that panel goes to 0. So we do our virtual slice in our section, then we can calculate QB 1, 2, QB 2, 3, etc. We've gone around the loop, calculated all of our QBs, but we're still left with this unknown value of QS0, which is where we started. Just like last week when we were doing it with integrals, this week we can do the same calculation with sums. So what we've got here is a moment equilibrium. So on the left we have the externally applied moment, which we've seen before, the shear force times the distance from the point we're calculating moments about. This is the moment for our basic shear flows. And this is the moment due to our constant shear flows. Now what are the terms? Well, they're the same meanings as we had last week. P is a moment arm to our shear flow, Q is our shear flow, and S is the distance on which it's applied. So again, we've got a distance times a shear flow times a distance gives us a moment. And on the right-hand side, we've got an area times a shear flow gives us a moment as well. Now this is written a couple of different ways. Let's just go back to our description here. Remember that if we've got any two booms, so these are our two booms here, and we've got a panel in between them, then we can work out the moment caused by that shear flow using this simple formula, sum of 2AQ. That's exactly the same here. So, as I've written in your online notes, sum of P, QB, S is equivalent to sum of, or twice the sum of the enclosed area times QB. So we'll do an example of that right now. And the first example we'll use is the one that we've already calculated. So this example up the top here. Now let's assume rather than being an open section, we're going to have a closed section instead. So all we've done is filled in the wall from point 4 to point 1. And one other bit of information that we need to know, which wasn't defined for the first problem because we didn't need it, is the exact location of that shear force that was applied. We said at the shear centre, but we never told you what the shear centre was. So for argument's sake, I'm now going to say that this is applied 100 millimetres from the left-hand web. Okay, so let's go through and work out what our shear flows are in this case. Now the first step, as I said before, we make our virtual cut and we calculate our QBs, and luckily we've already calculated those, so we don't need to redo them. QB 1,2 was minus 6 newtons per millimetre. QB 2,3 was equal to minus 12 newtons per millimetre. And QB 3,4 was equal to minus 6 newtons per millimetre. And if we want to be picky about it, QB 4,1 equals 0, because that's where we've made our cut. So as I've said, this is a moment equation, so we need to have a point about which we're taking moments. We need to have a starting point. Now, to make our life easier, let's just pick the middle of the web here. So we've got 1, 2, 3, 4. We'll pick in the midpoint between 2 and 3 at the neutral axis of the section. And we have to define which way is positive for moments. So we'll assume that because we've calculated our initial Q's in an anti-clockwise direction, we'll assume that anti-clockwise is positive. So about our origin, the externally applied force, the externally applied shear force, is acting in a clockwise direction. So we have a minus sign here. Now what does the moment equation tell us? Well, we know this part. We know the externally applied moment, and we can go through the calculation to work out this part. We know all the QB terms, we know the distances, we know the moment arms. We know the enclosed area. So the big unknown that we're trying to solve for in this equation is the constant shear flow. So it's the shear flow at our starting point before we cheated and cut the panel and made it 0. So we'll bring out these terms one by one just to make our life easier. So remember, we're taking these moments about an origin. So here's our origin here. What's the moment arm distance from the origin to our QB12? So for the basic shear flow in panel 1, 2, what's the moment arm to that? The geometry is up at the top if you... 200, yeah. So the first term in this is 200 is the moment arm. The Q is minus 6. And the S is the distance over which it's acting. What's the distance over which it's acting? 200 as well. The second term is for our QB23. What's the moment arm for 23? If we're taking moments about this point and we've got a shear flow acting in this web, there's zero moment arm. So we've got no moment arm there at all. Okay, so it doesn't matter what's in the rest of the term, it's zero. Now for 3, 4, so it's 200 times minus 6 times 200 again. Okay, so it's the same as the top flange. The top flange and the bottom flange are the same. So what have we got here? 400 times 6 is 2400, so minus 4800, unless I've made a complete mistake there. And what units have we got here? I know I've left units off, but what units have we got? This is a moment. We had millimeters, newtons per millimeter times millimeters. Just give us Newton millimeters, which is good because that's moment units. All right, so we've got everything we need. We know these bits. The hard bit here has been solved for us, so now we can find QS naught. So I'll just do a quick rearrange of the formula up the top there. QS naught equals, we're rearranging what we've got up there, so we've got minus SY xi, and I can never write that symbol very well, minus sum of PQBS all over 2 times the area. What's the enclosed area for this problem? We've got 400 on one side of the box and 200 on the other side of the box. Okay, 80,000. So let's put in our numbers and see what we get. SY is 4800. The moment arm for it is 100. We've got a minus here and a minus in the number that we worked out, so we end up with a plus. Okay, I've done some really bad maths up there. Some really bad maths up there. I need another couple of zeros on there. Okay. So what do you know? My pen's running out of ink again. Two times 80,000, but on the top, we've ended up with 0. So that was just dumb luck. That was a particular problem that I chose that ended up being 0. It's not always the case, and we'll see in a minute that it won't always be the case. So there's one more step of the calculation, and that's to calculate all the actual shear flows. So remember, that our shear flow in each section is the basic shear flow which we calculated plus the constant one which is acting around the section. So in this case, that's 0, so that's nice and easy. So our box section is here. Actually, I'll just draw them in the direction that they're actually acting. Okay. The only reason that ended up 0 is because I happened to pick the number 100 here, and if I'd picked any other number, we wouldn't have ended up with 0 in that for QS0. If you've got a non-zero QS0, you have to add it to each of the QBs that you calculated. Okay. So the problem to test your skills out is the tutorial problem, and I've got an adaptive tutorial for this particular problem. So you can go in and it'll give you a randomized version of this with your own dimensions and your own values. And every time you try it, you should get a new randomized version, hopefully. And this is a little bit more complicated than the problem that we've just done on the board, but it gives you some step-by-step instructions as to how to go through it. One little bit of geometry trickery which you will need to solve this problem. All the examples we've done so far, it's been very easy to find the moment arms and the distances and the areas. For these slanted sections, it can be a bit trickier to find moment arms to those. So one trick you can use is if you've got a triangle, I'll give you a formula for the area of that triangle. Okay, so if A is at the origin at 0, 0, then the area of that triangle is just given by this simple formula here. So when we have to do, if the Q was acting out here, then the area swept out, the enclosed area, is given by that formula. Okay, so just keep that handy when you're doing problems that have got a little bit more complicated geometry than the one we've done here. And always keep in the back of your mind the three-dimensional representation of what we're doing. We've idealized our structure from being skins and stiffeners to booms and panels. And in those panels, the shear flow is constant. So we can, in 3 dimensions, anywhere in the panel, if we test the shear flow, it'll be the same value. Okay, so if you need to do equilibrium in the 3rd dimension, that's fairly easy to do. And we'll do some examples of that in other lectures where instead of assuming that the longitudinal shear flow is constant, we'll vary it by varying the forces in the booms. So if we start applying other forces to the booms, we can start working out what happens to the shear flow in those panels. And so we can build up more complicated structures that way. We'll do, because we've got about half an hour now, we'll do one more complicated example to tie everything together. And I won't necessarily go through all the numbers here, I'll show you the procedure, but it'll tie together what we did at the start of the lecture with bending and what we've done for the second half of the lecture with shear, and then we'll look at potentially this question down the bottom, which is always a complicated one. What's the maximum von Mises stress? And the example ties together bits from Meg's an example. It's at the start of chapter 22. So I've jumped ahead a couple of chapters to get a more realistic problem. So this is our idealized fuselage section. So if we skip back, sorry, I'm going to make everyone feel a bit sick for a second while I skip back through the notes. I overshot it. Okay, so here was our idealization procedure. We took a complex structure that has skin and stiffeners in it, and we turned that into a simpler structure that has booms and panels. The first step was to work out the areas of all of our booms, which was a fairly simple calculation, which we did in a table. Then, for a bending stress, all we have to do is work out the second moment of area of the section, and then we can work out the bending stresses. That's fairly simple. Now, the next step is to apply what we've just learnt to, instead of just having a straight bending moment on the section, if we had a combination of bending moment and shear, we can calculate the shear separately, calculate the bending separately, and then add those two up through superposition. So the first step is to calculate the shear component, because we don't have values for that yet. And let's go through the procedure to do that. And I'm not going to try and replicate exactly the picture on the board. I'm probably going to have the wrong number of booms. I'm not counting. So, the first step is to calculate the IXX, which we've already done because we've done that for the bending calculation. So we don't need to repeat the calculation, it's still there. Now, because we've got a closed section, what's the first step to start the problem? Make a cut. So you can make a cut anywhere. As you've practiced a few of these, you'll start learning where to make the cut. But for argument's sake, we'll make the cut here. Okay, actually, given that the numbering scheme gives us a nice place to make the cut, we'll make the cut there. Okay, that just means you've got a nice, easy numbering scheme to calculate things with. Okay, so we've made the cut. And remember, it's a virtual cut. We're not really slicing down our fuselage. We're just, for the moment, setting the shear flow equal to 0 at that point. Now, the next step is to find our basic shear flows, find our basic values of Q. So, the procedure for doing that is the one that we introduced sort of midway through the lecture. QB equals minus the externally applied shear force over the second moment of area times the sum of BR, YR. Where each one of these sum terms is as we step around the section. Okay. So this is an identical problem to, say, the C-beam we did earlier. It's just got more steps in it. And in your table, you've already got your B's and R's in your tables, or B's and Y's in your table. So you can just have another column in your table to calculate all these bits, all these terms here. Okay. So we can do that. Now, what's the next step? Okay, remember with the closed sections, we had to find moment equilibrium. Okay. So find QS naught from moment equilibrium. Now, where's the best place to take moments for this problem? Right in the center. Okay, because it makes all of our moment arm or our area calculations very simple. Because it's always the same distance to every panel. If we took moments about somewhere else, for every single panel we would have to work out the moment arms and the areas, and it'd be very complicated. If we choose the center of a circular problem, all of that drops out. Because at some stage we're going to have either sum of P, QB, S, or twice the sum of the enclosed area times Q, B. Both these cases are made much simpler if you take the equilibrium in the center. Either this is constant or this is constant and can be taken out the front of the equation. You can do that. And then we can find QS from QB plus QS naught. So this is just a sum. And there's a nice table structure defined in MEGS, and I don't have the board space or the pen time to draw it all up, but there's a nice table that you can use for your own calculations, or you can use in Excel. A lot of these calculations lend themselves very well to automating in numerical methods. So we can do them in Excel or MATLAB or any other code that you choose to learn, but they're the ones that we teach you. So once you've got to this stage, we know at any point in the section, we know the shear stresses and the direct stresses. So I'm just going to draw a section of it here. Okay, so right from back in early in the class, we worked out that sigma Z1 was, say, 300 megapascals approximately, and for the number 16 and 2, it was about 280. Okay, and I'm just trying to dig out the numbers from Megson for the others, because we didn't go through the full calculation. Okay, so this here is Q12 is 16.1 newtons per millimetre, and there's 0 in Q16.1. Now, obviously each panel that you go to, these numbers are going to be different. So what does this tell us about stresses? Well, remember this is just an idealisation. When we made these booms, we were actually taking material from around here and plonking it into an idealised area. So if the stress on that boom is 300 megapascals, then the stress around that boom as well is also close to 300 megapascals. If we wanted to work out the direct stress, say here, we could interpolate between 280 and 300 based on the Y position to get a stress. Equivalently, our shear flow we've assumed is 16 newtons per millimetre constant, but it's also a simplification because in reality when there's skin here, that's varying as we go along. We'll, in a few minutes, see a way of improving our approximation there. But what that tells us, if we took a little element of material, let's just say we take a little piece of material out of here, and I'm going to exaggerate the curvature just so you can see the curvature direction. Now that little element of material has a tensile stress of what? What's the tensile stress? Oh, it's close enough to 300 megapascals. And the shear stress acting on that What's the shear stress? How do we get from shear flow to shear stress? Tau equals Q divided by the thickness. So the thickness was 0.8 millimeters. So 16.1 over 0.8, somewhere about 20. Okay. So on the sides, we've got about 20 megapascals. So at each little element of skin, we can actually go along and work out as we go around our fuselage section what the von Mises stress is. Because we know from the solid mechanics lectures early on that you can do a Morse circle on this problem. If you've got a direct stress and a shear stress, you can work out all sorts of things from the Morse circle. You can work out the principal stresses, the von Mises stress, the maximum shear stress. So at each section as you go around the barrel, you can add the shear stresses and the direct stresses and work out what the von Mises stress is. One other thing you can add to this is if you've got pressurization, if you've got hoop tension due to pressurization, you can also add hoop stresses. We know how to calculate hoop stresses as well because you've had lots of tutorial questions about that. So now you've got the tools to take a fairly complicated structure like a fuselage, which is one single cell, open cell, idealize all the internal structure, and work out what the stress is pretty much anywhere. So you now are some way towards being a stress engineer. If someone gave you a particular type of fuselage, you could actually solve what the stresses are in the structure. And if I go right back to the beginning, which is what we used, the thing that we used to introduce this lecture, okay, there's a fuselage there. A zoomed in version of the fuselage is in the top right. Okay. You could go in and tell me what the stresses in this panel are, what the stresses in this panel are, what the stresses in this panel are, and what the direct compressive or tensile stresses on the stiffeners are. Okay, so you've got a toolkit now to actually go and start doing that analysis. And the assignment, which I'll have up hopefully by the end of today, and everyone intake a breath when I mention assignment. The assignment will be a fuselage analysis like this. I'll add a few curly bits into the tail, such as tapering the fuselage. The fuselage won't be a nice straight barrel section. There'll be a taper to it, and we'll learn how to do tapered sections soon. But you can make progress towards the assignment without including the taper. And I'll give you some geometry for a fuselage, some moments and some forces on that section, and then you can go in and actually work out what all the boom idealization, what the stresses in the panels are, what the stresses in the members are. And when we learn about instability in a couple of weeks, you'll also, or not a couple of weeks, probably about 4 weeks, you'll be able to do some initial calculations to tell me whether the panels will buckle or not. Okay, so it will tie together everything from solid mechanics all the way up to here and including the next couple of lectures. So the assignment really has pieces from all the things you've learnt so far. One last thing I want to introduce before we all leave is just a concept. I won't do any calculations. We've made a lot of assumptions to get to this point. If we wanted to pick a position in this panel, we know the stress here is 300 megapascals and the stress here is 200 megapascals. And we've got a reasonable way of interpolating between the two. For our shear flows, our interpolation is not that good because we've got 16 here, we've got 0 here, we might have 30 in the next panel. It's not an easy thing to do the interpolation because the stiffeners are going to affect our calculations quite a bit. So what I want you to have a think about before doing the assignment is there a good way of checking whether our assumption that the shear flow in here, the assumption that the shear flow in here is constant, is there a way of checking whether that's a safe assumption? One way that we could do it is potentially to add some more booms and then work out how the shear flow varies between all those booms. Another way to do it would potentially be to reverse this calculation process somehow. Is there a way that we can go from, instead of being in this direction, could we reverse the problem? Could we make some anti-simplifying assumptions to make sure that our calculations are sensible?